Hey, welcome back from Thanksgiving break. Before the break, we had Veterans Day, and thank you for your service. Thank you for that as well. Just thinking about that whole combination of holidays for us, and I wanted to express my thanks for what you do as your career and how you're working your way to, further that in the apprenticeship program. So, we're going to jump in and start doing balanced equations. What we learned so far in terms of chemistry has been that we learned that there were elements and got the hang of their names and the naming systems of the polyatomic ions and how they get together as compounds. We saw that their electrons are on the outside, the protons and neutrons on the inside. Where the electrons are in the outermost shell is the most important part about how they react. And so we've seen, at least at that small level, how those atoms get together. How do we keep a track of that, though, when we're trying to make the reactions happen like an accounting system so that we can determine how much energy or how much products we want to use? Well, that's going to be through a balanced chemical equation. An equation has two parts, a left part of this arrow signal and the right part of this arrows. This is called a yield sign. So what you have is what you start with and you mix together. These are the reactants. Okay, in a recipe, it'd be the ingredients. And in the recipe, what you make is your product. If it's a cake or a meal or whatever. That's going to be what you produce on the right side. Produce on the right side, and the reactants are on the left. So usually when you see these are written out, you're going to notice the chemical symbols, but there's a few more, like the S and the G and the G. Those are going to be the phases that that substance is in, liquids, solids, gases. They are going to be marked to tell you what you would expect when you see the reaction. These are gases that are being produced. Now, there are other symbols like, hey, a solid or salts, for instance, that's thrown into water. A lot of times that's going to happen where you dissolve something in water. That's going to be shown as aqueous. Maybe something doesn't react completely one direction and it can fall back apart and come back. So that could be reversible. It's not as often. A lot of times reactions are one way, but not all are. There could be no reaction. You throw everything together and it doesn't work, so you just say no reaction. That's possible. Like you've seen up here already, gases are going to be another symbol, but sometimes we'll use an upward arrow in a reaction, so just so you get used to this, you can use that. That's a little faster to write in. Things that change color, all of these are going to be evidence of a reaction happening. If you see some kind of color change, that's absolutely chemical reaction. Usually that's enough to hint that things are going on. You might see something going from clear, all dissolved, and then all of a sudden it becomes milky or cloudy because you can't see through it. There's little particles in there. They may have not settled out yet, and so they'll look like you can't see through it. That's a key idea that there's something happening, and that's called a precipitate. It's usually a downward arrow. You may not see it actually collect at the bottom because it's so fine and hasn't sifted out. Other one is that energy is given off. So energy is going to be given off either as heat absorption. You'll feel like it gets cold. The cold packs you may have had if you sprained an ankle or something, you put that on your arm. That's a good example. Others are like the heat pads that you can put in your gloves in the winter. If you kind of rough them up, it's got some iron in there, and as it rusts, it actually warms your hands up for several hours. Light could be given off, like at those concert sticks that you break if it's like out on the road and you're trying to keep people from seeing, keep people seeing you so you don't have an accident, or it's a concert or something. You've seen those happen. They have several hours of reaction going. Now, one thing to remember, that energy isn't made up. You're not creating energy. You're not getting it for free. It's been stored there, probably from the sun as a reaction to make something inside that plant. That when we burn it, or if it was like oil or coal or something like those, that was when it was living. It fell down, got buried, it became those energy compounds. Even this thing that glows was a special compound that they put together that when it reacts, it gives off its light because it had certain kinds of bonds. So energy is always conserved. You don't get energy for free. You're just collecting it from someplace that's been built up or stored. In a chemical reaction, we also take into account all the mass that is conserved. All the mass before the reaction here on the left side has to equal all the atoms that are on the right side. That was what helped Dalton to discover what the periodic table should have been organized by. So I'm going to write an example, and we'll follow through these rules to see how how you write a chemical reaction. First of all, write out any symbols for compounds where the starting materials on the left and the products on the right. Let's take two things like aluminum foil and let's put it in hydrochloric acid. So aluminum foil would have the symbol for Al, and hydrogen chloride is going to have the symbol HCl. And those two are going to be thrown into a beaker, let's say. Now, you might see some evidence of something happening because the aluminum would be shiny and it's going to start to disappear. So that's going to go in and start to react with this substance, and you'd also notice that there'd be some hydrogen bubbles coming out. So those are some examples. This is going to be a gas. This is going to be dissolved. It's going to be aqueous because it's going to go from something shiny to just disappeared into the solution. You won't be able to see it. This is aqueous as well, so those symbols would go in, and aluminum is going to be a solid. Now, we have to give these all a charge, assign charges from the columns in the periodic table. If you remember, we'll go over here real quick. Aluminum is right here, and it's a +3. Hydrogen's +1. Chlorine over here is a -1. So we're going to remember those to put those in this example. Here. So let's add +3 for the aluminum, +1 for the hydrogen, -1 for chlorine, +3 for aluminum, -1 for chlorine, and +1 for hydrogen. Okay? So, aluminum's alone. It's not partnered with anything, so we don't have to worry about the plus or minus. It's just alone. That's fine. It can be alone. HCl, +1, -1, those look balanced. Okay? So that's, oops, I'll use that up. And they're balanced. Aluminum's +3, chlorine's a -1. That is not balanced. So what I have to do, if you remember, the easy way to do this is pull that number that's charged and put it as a subscript. I don't need a 1, but I'm going to need 3 here. So it's AlCl3. And then hydrogen's alone. And I'd normally say, well, leave it. Except that it's one of the magnificent 7. Those that always are diatomic. Hydrogen plus number 7 in the periodic table is nitrogen, oxygen, fluorine. Makes a 7 in that corner of the periodic table. So nitrogen, oxygen, fluorine, chlorine, bromine, astatine. So these always come in 2s. I have to balance it out that way. So what I've done is I've signed all the charges from the table. I've changed the subscripts, which is these numbers underneath based on what they need, what they're partnered with. Made all the diatomics, you know, all those that are diatomic, we made those. And then without changing any subscripts now, once we've done with this, so Al, HCl, AlCl3, and H2, they've been balanced. We're going to now balance the left side and the right side. This is the new kind of balancing we're talking about so that matter is conserved. 1 aluminum, 1 aluminum. I'm just going to start from my left and work my way through this, okay? Now, it does say start in the element that doesn't have multiples. Like if aluminum was here, here, and here, there are 3 places, leave that for last because they balance themselves out usually if you take care of just those that show up once. But everything in here only shows up once on the left, once on the right. 1 aluminum, 1 aluminum. 1 hydrogen. Ooh, there's 2 hydrogens over here, so I'm going to just throw in a 2 real quick. Okay, that balances, so I have 2 hydrogens in both places. Ooh, I've got 3 hydrogens here, but only 2 because of this. The 2 makes both of these into 2, so let me see if I can get rid of this. Okay, I'm going to delete that. What I really need is the lowest common multiple of 2 and 3, because I need to have that go into there 3 times. So 2 and 3 have a multiple of 6 that they both can go into. If I make this a 6 instead, and I make 6 chlorines, then I have to have 2 of these over here. So I have 6 chlorines there. So I can choose 6 chlorines and have this one to be 2 times that 3. That's 6 chlorines there. But that's still goofed up my hydrogen. So you still have to kind of go back and forth until these all get taken care of. Now I have 6 hydrogens, everybody's happy. Okay? That's the process I want you to go into your problems and give them a try, all right? As a matter of fact, I'll do one more for you. Let's just go to the worksheet if you would. Let me choose this one because it's a little bit more of a trick. I'm going to do this number 2 here, and I'll leave you to work some of these other. But this is one way I can say 1 potassium, 1 potassium. 1 chlorine, 1 chlorine. But here I've got a weird combination. 3 oxygens, 2 oxygens. I could think about, hey, how can I get the least common multiple? That's one way to do it. And another trick I've kind of learned over the years is say, hey, if I cover up that oxygen, that diatomic, and I say there's 3 more over here, if I take half that number, it actually works. And I'm going to write it in a weird way so that it's down here so I can get rid of it. So I took 3 halves oxygens. That would really give me, you know, these 2 end up canceling. That gives me 3 oxygens. That's 3 oxygens. Now, the crazy thing is you can't chop that molecule in half. It just got me the right proportions. So to get rid of this 2, I'm going to double everything. It's like doubling the recipe. Double here, and double this, which gets rid of that. And so really that's 2, 2, and 3. That's one little trick you can use. Or if you just thought, oh, you know what, the least common multiple is 2 and a 3 on there, you can do it that way too. All right, let's get you some work time and work on those problems.